This is question number 15 from the 4.2 My Lab math homework. And y'all, this is one of the tricky ones because they give us a graph of f prime and they want us to get information off that graph and then use it to sketch a possible graph of f of x. Okay, so if I want to sketch a possible graph of f of x, what do I need? I need information about f prime and I need information about f double prime. The first derivative and the second derivative. So I'm going to create sign charts for that. Okay, so let's create sign charts for both of these. I know the problem says to organize our conclusions in a table, but I'm just going to organize it in sign charts. Okay, so if I have this information, these sign charts, I can use it to sketch a possible graph of the original function. But how am I going to get that information? Well, we're going to slow our brains down and say, okay, what information is this graph giving me? So I have an x-axis and an f prime of x-axis. So if I pick a point on this graph, for example, this point right here, let's see what information that point is telling me. So I'm going to get x information off my x-axis, and I'm going to get f prime of x information off my y-axis. So this particular point right here, okay, I went ahead and labeled the scale on my axes because the x-axis is counting by ones and the y-axis is counting by 50s. Okay, so now that I've done that, what information are we getting from this random point I just picked? Okay, so the x-coordinate is a -4 and the y-coordinate is a -100. So this is actually telling me this. When my input is -4, then if I put that input into the derivative, because my y-axis is f prime, when I put -4 into the derivative, I'm going to get a -100 out. So see how we read these ordered pairs on the graph? So every point on this graph is telling me information about f prime of x. So I can take information directly off this graph and put it onto this f prime of x sign chart. And on the f prime of x sign chart, we want partition numbers, right? That's where the first derivative is either going to be equal to 0 or that first derivative is going to be undefined, but this is a polynomial, so we don't have to worry about that case. I just have to worry about where the output is 0. So that's actually going to happen here and here. So this point right here, if I put -5, if I input that into my function, then if I input -5 into the derivative, see how the output or the height of the graph is going to be 0? Okay, so I'm going to put -5 on this sign chart, and if I put -5 into this f prime function, I'm going to get 0 out. So that's one of my partition numbers right there. And then again on this point, if I input a 10 into what's being graphed, which is f prime, I get a 0 out. That's what's happening. So again, if I input a 10, I'm going to get a 0 out, and that's putting 10 into what was being graphed, which was the f prime function. And then I can see, okay, let's just do some test points. What if I test out x equals -6 here? Let's try that. Here's x equals -6. See how I have to go up to hit the graph of f prime? That's a positive output. So all of these outputs are going to be positive until I hit 0. And then let's pick another test point. Let's try 0, where x is 0 here. So where x is 0, if I have to go down to hit the f prime graph, that's a negative output. So all these outputs are going to be negative in this entire region until I hit 0 again. All of these outputs are negative until I hit 0 again. Okay, and then I don't know, let's pick another one. Let's do x equals 11. So here's x equals 11. Oh, that one's kind of yucky because it's so close. I can pick anything in this region, right? So I don't know, let's pick 15 because it's a little bit farther out and just a little bit easier to read. So 11, 12, 13, 14, 15. Ooh, that one I can see. When x is 15, I have to go way down here to hit my f prime graph. That's a negative output. So all of these outputs here are negative. So my whole sign chart would be negative right there. Okay, and let's think about these mins and maxes. What is happening at these points? Well, I know there's a horizontal tangent line. That means the derivative is going to be 0, right? The derivative of the thing being graphed. So if f prime is being graphed, then its derivative is going to be 0 there. Okay? Actually, what is this saying? That if I just read this point, if I put 0 into f prime, that's an output of 250. But if I put 0 into the second derivative, then it's hitting 0 because the derivative, the tangent line of what's being graphed, so the derivative of what's being graphed is 0 there. And then same thing's happening over here. Again, if I put 0 into the thing being graphed, I have an output of 0, but its derivative, if I take the derivative of the thing being graphed, oh, not at 0, y'all, an input of 10 here. If I input 10, it's also going to be height of 0. So both of those are 0 there. Okay. The output of the graph is 0. So this is telling me the output of the graph of the function. So output of, well, I'll just put the graph because the function is being graphed, right? At x equals 10. And this one's telling me the derivative of the tangent line at x equals 10. Okay, there we go. So those are going to be my partition numbers. So I need a partition number at 0, and I need a partition number at 10. And again, I'm going to put in here the second, well, I can write it up here. The second derivative, if I put 0 into the graph, came out to be 0. And the second derivative, if I put 10 into the second derivative function, horizontal tangent line there. Okay, and then let's just see what's happening again with test points, right? With test points. So let's test something in this region right here, like -1. X equals -1. Okay, here's x equals -1. Let me change up my color here so I can see it. Here's x equals -1. It's this point on the graph. Now, the second derivative, this is the tangent lines of the f prime graph. So to get these positives and negatives, I have to look at the tangent lines. See how the tangent line would be pointing down there at this point? So I would have negative outputs. The tangent lines of the f prime graph, the derivative of the f prime graph, right, is negative there. Now let's pick another test point. I don't know, let's pick 5. Okay, let's go. Here's 5. Here's the point on the graph. See how the tangent line's pointing up in that region? So all of these outputs would be positive. And then we'll pick another test point. Let's stick with that x equals 15 since I already have that marked on the graph here. You know, x is 15. This point right here on my graph. See how my tangent line's going down? So it's going to be negative. Okay, so I've created these sign charts here. And I'm going to use just these sign charts to sketch a possible graph of the f of x function. I'm not going to use what was given to me anymore. It'll confuse me. Well, actually, before I erase that, let's just think about this function that was graphed using some algebra. Okay, so this general shape here, just based on my algebra knowledge, it's an odd function because see how the ends are pointing in opposite directions? So I know this is odd. So if I worked backwards, if I thought about reversing that power rule, I should get an even function out because you decrease the degree by 1, right? And this looks cubic to me, right? This looks like a cubic function. So if I worked backwards from that, let me move this down just for a little split second here so I can write above it. Okay. So if I worked backwards, oops, or not, there it goes. Okay. If I worked backwards from that, if I thought about, okay, what would my original function, what degree would it have been? Think about doing the power rule backwards. Well, if I drop my exponent down and decrease that number by 1 and I get something odd, like a cube, then this is going to be even. So when I sketch this f of x graph, it should be even. The ends are either going to both point up or the ends are going to be both pointing down, and there's could be some squiggly stuff in the middle, but at least I'll have a general shape. Like, so when I sketch this graph, I'll know if I'm even close to correct. But it should be an even function. So the main idea there, the ends pointing the same direction. Okay, so let's see if that actually happens. Okay, I duplicated those sign charts, and now I'm going to ignore this graph and only look at the sign charts. Okay, ignore that. Don't look at it. It'll mess you up. Okay, here we go. So let's sketch a possible graph here. So let's analyze our first derivative sign chart. What does the first derivative tell you about the original function? This is going to tell us our local extrema, that's your local mins and maxes, of the f of x function, and that's what we're graphing now. And then the second derivative sign chart, this is going to tell you your concavity of the f of x function. Okay, so let's look for our local extrema first. So I can see my tangent lines went positive, hit 0, and went negative again. So there's going to be a local max when x equals -5. So let's mark that on my graph. 1, 2, 3, 4, 5. And it's just a sketch. So I can place that local max anywhere on this vertical line. As long as it's lined up with the input -5, we're good. So that was what makes it a possible sketch. I don't know. I'm just going to put it right here. So let's make this our local max. So this will be our local max. Okay, so I'm going to have a horizontal tangent line there because when I put a -5 into the first derivative, I should get a 0 out. Okay, and then over here when x equals 10, my tangent lines were going down. It zeroed out, but then it went down again. See how that's not a local min or max? So when x equals 10, there's no local extrema there, but we're still going to mark that on our graph because I still go horizontal for a split second, right? So let's still mark that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, not drawn to scale. And all I know about this is if this is my local max, I just need to sketch that other point, you know, somewhere on this vertical line. I could even put it right on the x-axis if I wanted to, but I'm not. I don't know. Let's just put it right here. And again, my tangent line is going to go horizontal there, but it's not a local extrema, but I'm going to emphasize that horizontal tangent line there. Okay, and now let's connect those points on the graph with our concavity. So what's going on with the concavity here? Okay, so we know we need to be concave down in this region until I hit 0. Okay, so all this region here needs to be concave down. So I'm going to shade all this concave down. Anything I draw in this green shaded region, that needs to be concave down. And then I switch over to concave up between 0 and 10. That makes an inflection point here, right? Anytime you change signs, in this case from concave down to concave up, you have an inflection point. So this is an inflection point. And again, I don't know exactly where it's going to be. I know it needs to be between this local max and this other point that I plotted here. So I don't know, let's just, as long as it's lined up with my input being 0 in there somewhere. So let's just put it right at the origin. Why not? Let's put it right there. It's just a possible graph. As long as, you know, it's on this vertical line between those other 2 points that I've already plotted. So let's put it there. And again, I'm going to highlight that everything starting at 0 till I go to 10. So everything in this region needs to be concave up, and then I have another inflection point when x equals 10, which I've already drawn, right? So I have another inflection point right here. So this is also an inflection point right there. And it's going to switch back to concave down at that point. So this is going to go concave down, concave down, concave down. I should do it in green so I can be color coordinated. Concave up, and then concave down. Okay, so I will highlight starting at 10 forever, all this region, concave down. Okay, so now let's just connect those points to reflect that shape. So concave down until I hit this point. Okay, all this is concave down. And then I'm going to go concave up, and I need to really emphasize that I'm going to go horizontal for a split second there. So concave up. See how that's not a great concave up graph? So I definitely want to label that, concave up there. So I can see, the curve didn't look great. It kind of looks flat. But then I go concave down after that. Let me zoom out a little bit there. So then I went concave down. And again, this one's more obviously concave down, but I'll still label it. But here's that point. And I tried to emphasize it went horizontal there, but it doesn't look great. So I'm just going to label horizontal. The more you can label if your graph isn't looking like super awesome, the better. So let's see here. Let me get rid of all this. I'm going to try to make that a little more obvious. So horizontal, went concave down here, concave up. Okay, still not great, but it's just a sketch. And what I could have done also, if it's not working out great, remember I just arbitrarily put that inflection point. So maybe I could even lower it a little bit for emphasis, and still it would go horizontal there, but that might help me like really emphasize that concave up shape, concave down shape, and the fact that it went horizontal right there. But again, it's just a sketch. if you label it very well, then it's okay if your sketch isn't looking absolutely gorgeous, because your labels will help me grade it. Okay, so the important things on this graph of f of x is to make sure you label any of your local extrema or any point where your derivative is going 0. You know, you can put those horizontal tangent lines. That'll help. And then your concavity, if it's not blatantly obvious, make sure you're labeling the concavity. So, you know, this concave down region is pretty obvious, but I still labeled it. My concave up region was a little more subtle. And then I went concave down again. And notice, heads up, your ends are pointing the same direction. So using some algebra knowledge, that is definitely an even function, which is what we were expecting, our prediction from, you know, previously when we looked at that odd derivative. We should have an even original function there. But again, that's just to kind of check yourself. And I know these are tricky, y'all. I know. So please don't hesitate to take a picture of your scratch work and email it to me if you're struggling, and then I can help pinpoint where things are going wrong, okay? Because you'll definitely have a problem like this on test 3.